All right, so we've already talked earlier on in the course about acid-base neutralization reactions. All right, so if I react perchloric acid with sodium hydroxide, perchloric acid's a strong acid, it completely ionizes. Sodium hydroxide is a soluble hydroxide, so they completely separate. And in essence, the perchlorate ion is oh, what a non-base. Perchlorate is the conjugate of perchloric acid, so it has no basic property. Sodium ion has no acidic property. So in the end, H plus ions react with hydroxide to form water. In the end, you're left with water. Nothing in the solution is going to affect the pH except autoionization of water. If I react a weak acid, however, with a strong base, what I'm left with is a conjugate cyanide ion that has basic properties. So cyanide ion will react with water to form reform reform hydrocyanic acid and hydroxide. So in the end, you have a basic solution. All right. This neutralization, you're left with cyanide ion, and the cyanide ion will hydrolyze water to reform hydroxide. If I react hydrobromic acid with ammonia, a strong acid with a weak base, I'm left with ammonium ion. Ammonium ion is the conjugate acid of ammonia. And ammonium ion, because ammonia is a weak base, its conjugate is a significant acid. So ammonium ion will break apart in water to reform H plus ion. And as far as weak acids with weak bases go, it's going to depend how strong the weak base is and how strong the weak acid is. So I'm left with two conjugates, ammonium ion, which will make a solution acidic, and cyanide ion, which will make it basic. So which one is stronger, the cyanide ion or the ammonium ion in terms of affecting the pH? So it's a question mark. It depends on the strength of the ammonium ion and the cyanide ion conjugate base. Or I could, refer to that chart, right? Which is a stronger acid, ammonium ion or hydrocyanic acid, right? Equilibrium will lie to the side of the weaker acid. Acid-base properties of oxides and hydroxides. Well, we visited this earlier when we talked about acids, so this is kind of just rehashing it again. Um, Metallic oxides, when you put them in water, give bases. So metal oxides make hydroxides. Therefore, they react with acids. Oxides of nonmetals give acidic solutions. So nonmetal oxides make acids, like carbon dioxide makes carbonic acid, and sulfur trioxide makes sulfurous acid, and so on. And we didn't talk about this one, but aluminum oxide reacts with both acids and bases. So that's called being amphoteric, meaning you react with both acids and bases. All right, so I put this slide in here just to remind us, right, that oxide has a conjugate acid. The conjugate acid of oxide would be hydroxide. So it's almost a stupid thing to say because hydroxide is such a base. But yeah, you could potentially take an H off of hydroxide to make oxide. So oxide would be the conjugate base of hydroxide. So this is a really strong base, stronger than hydroxide. So if we were talking about, right, the Ka for this, meaning the equilibrium constant for this being an acid, is practically zero. So this doesn't go forward. So in the other direction, right, oxide reacting with H plus is extremely forward, all the way forward. So yeah, if you put oxide in water, you make hydroxide. So oxide, the H is taken off of water to put onto oxide to make hydroxide. And since you removed an H from water, right, the conjugate base of water is hydroxide. So as we said, right, metal oxides, when you put them in water, make hydroxides. And it's because of the oxide, right? The oxides reacting with the water. Sodium's role is a spectator. It's just there. Same with barium hydroxide, right? So, or it should say barium oxide reacting with water. You're making barium hydroxide. Again, well, all right, look, no, we got them as solids. All right, so hey, it wasn't aqueous, right? You put solid sodium oxide in, all right, so sodium's not a, you know, a spectator. It's liberated during the reaction. Same with the barium oxide. All right, metal oxides react with acids, right? So if you put barium oxide with nitric acid, the oxide will, take an H to form water. Oxides of non-metals give acidic solutions. So as we said, right, you have carbon dioxide, you put it in water, you'll make carbonic acid. You put sulfur trioxide in water, you'll make sulfuric acid. Tetraphosphorus decaoxide put into water makes phosphoric acid, and so on. So non-metal oxides make acids and oxyacids, right? So because you got an oxide in there. So they'll react with bases. So if you put carbon dioxide with sodium hydroxide, carbon dioxide will neutralize the base. I'm going to put this in just because it's with it, but we're not going to see this on the AP exam. If we have aluminum oxide, it'll react with hydrochloric acid. In that case, it's acting like a base. And aluminum oxide will also react with sodium hydroxide. So it'll react with both. So that's what it means to be amphoteric. All right, Lewis acid-base chemistry. This is a definition of acid-base chemistry that we didn't deal with before. And the definition of a Lewis acid is an electron pair acceptor. So this is kind of backwards to what we know as a Bronsted, right? Bronsted is a H plus donor. So in the Lewis definition, an acid is an electron pair acceptor. And whereas the base with a Bronsted definition was a proton acceptor, now with the Lewis definition, it's an electron pair donor. So if both electrons are coming from the one atom, right, the X here reacting with Y, right, and you're forming a covalent bond, both of the electrons are coming from X, none are coming from Y to make the bond. So this was a definition of coordinate covalent bonding, where both of the electrons are coming from one of the atoms. So coordinate covalent bonding is an example of Lewis acid-base chemistry. So the classic example is ammonia reacting with boron trifluoride. As we know, when you do the Lewis dot structure for boron trifluoride, you have to break the octet rule for boron because fluorine can't double bond. So you have an incomplete octet for boron. So if ammonia comes along, it donates an electron pair to form a bond with the boron. So now all of a sudden you went from sp2 hybridization with the boron in boron trifluoride to sp3 hybridization when it coordinate covalent bonds with the nitrogen, right? So in this situation, the electron pair donor is the base. The electron pair acceptor is the acid. All right, when we do the Lewis definition. All right, so when we just kind of skittered over, why? How does it work when you put CO2 in water to make carbonic acid? Well, it's complicated, right? It's an example of Lewis acid-base chemistry, and you form carbonic acid. So the way this is done, the mechanism for this is an electron pair is donated from the water to the carbon. All right, so the water is acting like the electron pair donor, it's acting as the base. The carbon is acting like the electron pair acceptor, it's the acid. This electron pair in the double bond jumps out to one of the oxygens on the periphery. And we end up with this intermediate. This is a very unstable molecule. An electron pair is donated from, internally from one of the oxygens to the hydrogen on that water that got attached. This thing doesn't look stable, right? We got an H2O group, right? An OH group, all right, but an H2O group, unstable. So the electron pair is donated by the one side of the atom to the other to form a bond between the hydrogen and the oxygen to form the carbonic acid. So CO2 bubbled into water to make carbonic acid is an example of Lewis acid-base chemistry. And we'll get into Lewis acid-base chemistry more later on when we talk about solubility equilibria. So that's later on in this unit.